The strategic situation confronting the German air defense in the late autumn of 1944 was characterized by a catastrophic and irreversible collapse of industrial logistics, particularly in the production and distribution of high-grade synthetic aviation fuels. The massive, coordinated bombing campaign executed by the United States Army Air Forces and the British Royal Air Force, specifically targeting synthetic oil refineries such as the massive complex at Luna, had effectively starved the Luftwaffe of the precious B-4 and C-3 kerosene fuels required to keep their conventional piston-engine fighters and revolutionary Messerschmitt Me-262 turbojets airborne. While the German aviation industry possessed highly advanced aerodynamic designs and fully operational jet fighters, these cutting-edge machines sat uselessly on grass airfields, camouflaged under forest canopies due to empty fuel tanks, creating a terrifying operational paradox where the Reich had reached technological supremacy but logistical bankruptcy. In this crucible of industrial starvation, the Reich's aviation research centers were ordered to seek alternative, unconventional propulsion methods that did not rely on petroleum distillates, forcing engineers to look toward raw, domestic materials that Germany still possessed in massive abundance, namely coal. It was within this desperate environment that the visionary aerodynamicist Dr. Alexander Lippisch proposed an aircraft concept that seemed to belong more to the realm of science fiction than practical wartime aviation: a supersonic delta-wing interceptor powered entirely by low-grade, granulated coal. The concept of coal-powered flight was not merely an eccentric scientific curiosity, but a calculated response to the realities of raw material scarcity, aiming to utilize Germany's extensive reserves of lignite and bituminous coal to fuel a high-speed defense interceptor that could defend the airspace above the remaining industrial heartlands. Under the official project designation Lippisch P.13a, researchers at the Luftfahrtversuchungsanstalt Braunschweig began investigating the thermodynamic feasibility of solid-fuel ramjets, initiating a series of highly unconventional combustion experiments to determine if a solid hydrocarbon like coal could be rapidly gasified and burned under the intense airflow of a supersonic intake duct. The technical challenge was unprecedented, requiring a complete reevaluation of jet propulsion physics, as the engineers had to design a combustion chamber that could sustain a stable, high-energy burn of solid fuel blocks within a moving column of compressed air without the engine choking or blowing itself out. By selecting coal, Lippisch and his team were attempting to bypass the entire petroleum supply chain, designing a defensive interceptor that could literally be fueled by the same cheap, raw energy source that heated German homes and ran their heavy manufacturing lines. This approach represented the absolute extreme of late-war German crisis engineering, representing a transition from the pursuit of military dominance to a struggle for raw survival, where the boundaries between advanced science and medieval energy sources became completely blurred. The resulting interceptor design was not a conventional aircraft modified to burn coal, but a highly integrated, aerodynamic flying wing built entirely around the massive internal dimensions of a solid-fuel ramjet engine, transforming the fuselage of the aircraft itself into a flying furnace. This design philosophy marked the Lippisch P.13a as one of the most intellectually daring and logistically desperate concepts in the history of aviation, illustrating how the absolute starvation of strategic resources can force scientists to pursue revolutionary, outside-the-box engineering solutions that challenge the very laws of conventional aerodynamics. The aerodynamic configuration of the Lippisch P.13a was a masterclass in pioneering delta-wing design, a structural concept that was decades ahead of its contemporary aviation peers. Dr. Alexander Lippisch had spent the interwar period researching tailless aircraft and delta-wing gliders, realizing that a pure triangular wing form offered significant structural and aerodynamic advantages, particularly as aircraft speeds began to approach the sound barrier. For the P.13a, Lippisch designed a radical delta wing with an aggressive 60-degree sweepback angle, a configuration that minimized wave drag and provided exceptional structural rigidity without the need for heavy, steel wing spars that Germany could no longer manufacture. Because the aircraft was designed to operate at projected supersonic speeds reaching up to Mach 2.6, the thick, swept triangular wing acted as a natural shock absorber against the violent compressibility effects that tore conventional straight-winged aircraft apart, transforming the wing itself into a highly efficient aerodynamic lifting body. To minimize drag and maintain a perfectly clean aerodynamic profile, Lippisch made the radical design decision to integrate the pilot's cockpit directly inside the root of the massive vertical stabilizer fin, rather than mounting it as a traditional bubble canopy atop the fuselage. This arrangement meant that the vertical stabilizer was not merely a control surface, but an active structural housing for the pilot, who sat encased in a heavily armored, streamlined enclosure that merged seamlessly into the main triangular silhouette of the aircraft. This integration reduced the overall cross-sectional area of the interceptor to an absolute minimum, a critical factor for achieving supersonic speeds with the limited thrust profiles of early jet propulsion systems. The canopy itself was designed as a low-profile, flush-mounted glass assembly, offering the pilot a limited but necessary forward view over the sharp nose intake of the ramjet, while the thick wooden and steel structure of the vertical stabilizer offered excellent protection against the defensive machine gun fire of Allied bomber formations. Due to the extreme strategic shortages of light alloys like aluminum and duralumin in late 1944, the structural composition of the Lippisch P.13a relied almost entirely on non-strategic materials, primarily high-grade plywood, pine, and structural adhesives. The entire skin of the delta wing and the vertical stabilizer was to be constructed of molded plywood skins bonded over a wooden framework, a manufacturing technique that allowed the aircraft to be built by local woodworking shops and cabinet makers rather than specialized, heavily bombed aviation factories. This reliance on wood did not compromise the aircraft's supersonic ambitions, as the high strength-to-weight ratio of bonded plywood, combined with the inherently rigid structural geometry of the delta wing, provided a remarkably robust airframe capable of withstanding the immense aerodynamic pressures of high-speed flight. By combining futuristic supersonic aerodynamics with traditional, low-cost woodworking techniques, Lippisch created a design that was simultaneously highly advanced and remarkably practical for a nation on the brink of total industrial collapse. At the heart of the Lippisch P.13a was its most controversial and brilliant technical feature, a solid-fuel, coal-powered ramjet engine designed to generate high-speed thrust without a drop of traditional petroleum fuel. Developed in close collaboration with the renowned aerodynamicist Dr. Karl Güterle and combustion experts at the Luftfahrtversuchungsanstalt Braunschweig, the engine was built entirely around a large, rotating, circular wire mesh basket situated in the center of the main internal air duct. This basket, measuring several feet in diameter, was filled with a dense charge of granulated or pressed block coal, specifically low-grade lignite or brown coal, which was highly abundant within the German domestic mining network. As high-velocity air entered the nose intake of the aircraft, it passed through a diverging duct that slowed the air down, converting its kinetic energy into high pressure and compression, which was a critical thermodynamic prerequisite for sustaining efficient ramjet combustion. To understand the combustion physics of this unique power plant, one must analyze the dual-phase process of gasification and ignition that occurred inside the moving airstream. As the granulated coal was ignited using a small auxiliary liquid fuel burner or a localized gas torch, the intense heat caused the solid coal blocks to rapidly gasify, releasing a highly combustible stream of carbon monoxide and volatile hydrocarbon gases directly into the secondary combustion chamber located downstream of the rotating basket. This gaseous fuel mixture then blended with the high-pressure oxygen rushing through the air duct, initiating a continuous, self-sustaining thermodynamic burn that generated immense thermal expansion. The resulting superheated exhaust gases were then accelerated and expelled through a convergent-divergent nozzle at the rear of the aircraft, producing a steady, powerful stream of thrust that pushed the delta wing airframe forward. To ensure that the coal burned evenly and did not choke the airflow, the wire mesh basket was designed to rotate slowly at approximately 60 revolutions per minute, driven by a simple, reliable mechanical linkage or a small air turbine, which continuously exposed fresh, unburned coal surfaces to the incoming air while centrifugal force helped clear away the spent ash. The engineering calculations conducted by German researchers suggested that this coal-powered ramjet was not merely a desperate stopgap, but a highly efficient thermodynamic engine capable of sustained supersonic operation. The granulated coal charge, weighing several hundred kilograms, could provide enough high-density thermal energy to sustain flight for up to 45 minutes, which was more than enough time for a high-speed local interceptor to climb and engage Allied bomber formations. Furthermore, because coal contains a high concentration of carbon, the energy density per unit of volume was remarkably high, and the physical stability of solid coal eliminated the risk of catastrophic fuel tank explosions that plagued early liquid-fueled rocket interceptors like the Messerschmitt Me-163. The primary engineering challenge lay in managing the intense heat generated by the coal furnace, requiring the integration of cooling ducts that routed cold boundary layer air along the inner wooden walls of the fuselage, a design that effectively shielded the wooden structural framework from the blistering temperatures of the internal jet stream. Despite the thermodynamic brilliance of the coal-powered ramjet engine, the Lippisch P.13a faced a fundamental, systemic physics limitation common to all ramjet-propelled aircraft. The engine produced exactly zero static thrust. Because a ramjet relies entirely on the high-speed forward motion of the aircraft to compress the incoming air before combustion, it is incapable of generating any thrust while sitting stationary on a runway, requiring a separate, high-energy launch system to accelerate the interceptor to its minimum operational ramjet speed of approximately 320 km per hour. To overcome this critical operational hurdle, German engineers proposed several highly complex and hazardous launch configurations, the primary option being a massive, rocket-powered launch sled that would slide along a long, steel monorail track. The interceptor would be secured to this heavy sled, which would be propelled forward by a cluster of powerful solid-fuel booster rockets, accelerating the wooden delta wing down the track until it achieved sufficient airspeed for the internal coal furnace to ignite and take over propulsion, at which point the aircraft would detach and climb steeply into the sky. An alternative launch concept involved attaching disposable, liquid-fueled Schmitting booster rockets directly to the underside of the delta wing, which would ignite to provide the initial takeoff thrust from a simple, inclined ramp. These booster rockets would burn furiously for several seconds, launching the P.13a into the air like a missile, and once their fuel was completely exhausted, the pilot would pull a mechanical release lever to jettison the spent metal canisters, leaving the aircraft to fly cleanly on coal power alone. For landing, the P.13a omitted a conventional, heavy-wheeled landing gear to save weight and maximize aerodynamic efficiency, relying instead on a retractable, steel-reinforced wooden skid mounted along the centerline of the belly. After engaging enemy bombers and exhausting its solid coal charge, the interceptor would glide back to Earth as a powerless wooden glider, landing at a high touchdown speed on its central skid upon the grass airfields of the Reich, utilizing a pneumatic braking shock absorber to bring the lightweight machine to a halt. This launch and landing profile introduced immense tactical and physical risks that made the P.13a an incredibly hazardous system for Wehrmacht pilots. During the powerless glide back to base, the unpowered delta wing was an incredibly slow, vulnerable target, making it easy prey for Allied fighter escorts like the P-51 Mustang, which frequently patrolled German airfields to shoot down landing jets and rockets. Furthermore, if the rocket-boosted takeoff failed or the coal ramjet failed to ignite in midair, the pilot had almost no altitude or speed to recover, turning a high-stakes interception mission into a potential suicide flight. The sheer complexity of deploying a fleet of rocket sled-launched, coal-powered, wooden gliders in the middle of a collapsing war zone highlights the profound disconnect between the advanced laboratory calculations of German scientists and the chaotic, war-torn reality of late 1944. While the powered, coal-burning Lippisch P.13a remained a paper project, its revolutionary aerodynamics were materialized in a physical, full-scale test glider designated the Lippisch DM-1, an aircraft that undertook an extraordinary journey from a war-torn German hangar to the premier research facilities of the United States. to validate the low-speed stability and handling characteristics of the radical 60-degree delta wing shape before committing resources to a supersonic prototype. Dr. Alexander Lippisch mobilized the student members of the academic gliding groups at Darmstadt and Munich, known as Akaflieg Darmstadt and Akaflieg München. Under the direction of Lippisch and his engineering assistants, these young students began constructing a sleek, unpowered wooden glider that perfectly matched the external geometric dimensions of the projected P.13a interceptor. Utilizing their extensive expertise in high-performance wooden sailplane construction to assemble a highly refined aerodynamic testbed. The construction of the DM-1 was a desperate race against time, conducted in hidden hangars and workshop facilities as the Allied ground armies pushed deep into the heart of Germany. In May 1945, troops of General George S. Patton's United States Third Army captured the Prien airfield near Lake Chiemsee in Bavaria, discovering the nearly completed wooden delta-wing glider hidden under camouflage netting inside a hangar. Recognizing the immense aerodynamic value and futuristic potential of the design, American military intelligence officers immediately halted any scrap or demolition orders, placing the German students and engineers under armed guard and ordering them to resume and complete the construction of the DM-1 glider under strict United States military supervision. Once completed, the wooden glider was carefully crated, loaded onto a transport ship, and sent across the Atlantic Ocean to the National Advisory Committee for Aeronautics, or NACA, at the Langley Aeronautical Laboratory in Hampton, Virginia, which is the historical predecessor of modern-day NASA. Upon its arrival in 1946, the DM-1 was mounted inside NACA's massive full-scale wind tunnel, where American aerodynamicists conducted a series of highly intensive wind tunnel tests to unlock the secrets of German delta-wing physics. The initial wind tunnel runs revealed that the thick, blunt leading edge of the glider's original wing caused significant drag and stall issues at low speeds, prompting NACA engineers to make critical structural modifications, including sharpening the leading edges and adding experimental nose flap extensions. These modifications dramatically improved the glider's lift-to-drag ratio and stall characteristics, proving to American aviation researchers that the delta-wing layout was not a dangerous gimmick, but a highly stable and efficient aerodynamic platform for high-speed, and eventually supersonic, flight. The rigorous testing of the DM-1 glider at Langley dismantled the skepticism surrounding tailless aircraft designs, providing American engineers with a treasure trove of empirical aerodynamic data that would reshape the trajectory of post-war military aviation. In a cold, analytical strategic assessment, the Lippisch P.13a program was a magnificent, desperate failure as a practical wartime weapon, yet it became one of the most influential aerodynamic catalysts of the early supersonic jet age. Had the war continued into 1946 and the German industry managed to produce a small fleet of coal-powered interceptors, their tactical impact would have been practically negligible, suffering from the same systemic limitations that doomed other late-war German wonder weapons like the rocket-powered Bachmann 349 Natter. The Wehrmacht lacked the highly trained pilots required to fly a high-speed delta wing. The coal-burning ramjet would have had serious thermal endurance issues, and the logistical nightmare of maintaining solid-fuel rocket-sled launchers under constant Allied air interdiction would have paralyzed operations before the aircraft could even take off. In the final analysis of combat viability, the P.13a stands as a prime example of late-war German over-engineering, representing a brilliant thermodynamic answer to a fuel crisis, but a completely impractical weapon for the real-world battlefields of World War II. However, the scientific legacy of the fire triangle bypassed its wartime failure, soaring directly into the designs of the most advanced supersonic aircraft of the Cold War. The empirical aerodynamic data collected by NACA from the wind tunnel testing of the Lippisch DM-1 glider was shared directly with American aerospace defense contractors, most notably Consolidated Vultee, known as Convair. Convair's chief aerodynamicist, having studied the NACA reports, realized that the 60-degree delta wing shape was the key to conquering the sound barrier, directly incorporating the Lippisch layout into the experimental Convair XF-92 jet research plane. This research line led directly to a legendary family of American supersonic delta-wing aircraft, including the Mach 1 Convair F-102 Delta Dagger interceptor, the Mach 2 F-106 Delta Dart, the Radical Convair F-2YC Dart Delta Wing seaplane, and the supersonic Convair B-58 Hustler strategic bomber, all of which traced their structural ancestry back to the wooden glider captured at Prien. Beyond the United States, the delta wing concepts pioneered by Lippisch in his desperate pursuit of coal-powered flight spread across the globe, deeply influencing European aviation programs. In France, aircraft designer Marcel Dassault embraced the delta wing geometry, creating the iconic Dassault Mirage 3, Mirage 4, and Mirage 2000 series, which became some of the most widely exported and successful supersonic combat jets in history. In the United Kingdom, the Avro company utilized delta wing configurations to build the majestic Avro Vulcan delta wing strategic bomber, demonstrating that the structural and aerodynamic layout designed by Lippisch for a tiny, coal-fired furnace could be scaled up to lift a massive, nuclear-armed strategic bomber. Ultimately, while the Lippisch P.13a never flew on the power of burning coal, its aerodynamic geometry conquered the skies of the post-war world, proving that the frantic, desperate engineering born of a nation's death throes can sometimes forge the path to the technological future.